Hello everyone, I'm Mert and I'm going to talk about Diffie-Hellman key exchange vulnerabilities. So the vulnerability that I'm going to talk about was described by Adrian et al. In 2015 in a paper, and the protocols that use Diffie-Hellman key exchange include SSH, IPsec, which is used by some VPNs, as well as transport layer security. So some HTTPS sites are vulnerable as well. Firstly, I want to quickly describe and demonstrate Diffie-Hellman key exchange. It is an example of public key cryptography, and in that sense, it's similar to the RSA algorithm. And in the demonstration there is Alice and Bob. They want to communicate secretly without anybody eavesdropping, so they need to use cryptography. We start with numbers G and P. G is our base number and P is a prime number. Then, using his secret integer A, Alice calculates G to the power A mod P, which is X, and makes that public. Similarly, Bob calculates Y, which is G to the power B mod P, B being his secret integer, and then he makes Y public. Then Alice takes Y and calculates Y to the power A mod P, which is the secret key, and then Bob calculates X to the power B mod P, which is again the secret key. These two numbers are the same. This is based on the fact that the order of the exponents doesn't really matter, doesn't change the outcome, even when there is modulo operations involved. Therefore, without making any important information public, Alice and Bob can exchange keys. To uncover the secret key, we would basically need to calculate either the secret integer A or the secret integer B. And that's not an easy task. It would require us to find X given G to the power X modulo P equals Y. And to find that, we need to calculate discrete logs. To calculate discrete logs, we have a family of algorithms called number field sieve algorithms, NFS. And as you see in the picture that I took from the paper, it consists of 4 stages. What is important to us and important to the exploit is that the first 3 stages only require the prime number P for the calculations. So what we can do is use the number P and make these calculations beforehand and record them in a database, and then at the time of the exploit we can use that information to uncover the secret integers, which in turn gives us the secret key. The 4th stage of this algorithm takes remarkably less time than the first 3 stages. As we can see, the prime number P is an important part of the security of this algorithm, and larger prime numbers are considered more secure. As I mentioned before, transfer layer security or TLS protocol uses Diffie-Hellman key exchange among other key exchange algorithms, and it allows prime numbers of size 512 bits, 768 bits, 1024 bits, or even larger primes. However, today 512 bit primes are not considered secure. The problem arises from policies of the United States through the 90s, where there were heavy restrictions on cryptography exports, and as a result, prime numbers larger than 512 bits were not allowed. So to this day, for purposes of backward compatibility, some servers still accept 512-bit primes for Diffie-Hellman key exchange. So I first want to go through how a regular TLS handshake works. So we want to establish a secure communication between a client and a server. Firstly, the client sends the client hello message. This contains, among other things, a list of key exchange algorithms that the client can perform. In the example, we see that Diffie-Hellman is in that list. The server responds by a server hello message, and the message contains the specific algorithm which the server has picked to perform the key exchange. It also sends the server key exchange message, which contains a signature that has the prime number P, the base number G, as well as the calculated G to the power B. The client responds with the client key exchange message, and that contains G to the power A. So now both sides have everything they need to privately calculate the secret key, and using that key, then they can establish a secure encrypted communication. Logjam exploit uses a man-in-the-middle attack, which means a malicious computer pretends to be the server when communicating with the client and pretends to be the client when communicating with the server in order to intercept the communication between them. Again, the client sends the client hello message, which is intercepted by the man in the middle. And lucky us, among the key exchange algorithms listed, there is regular Diffie-Hellman. If that is the case, then the man in the middle removes all of the listed key exchange algorithms and puts in their place export grade Diffie-Hellman only. As we went through it before, export grade Diffie-Hellman uses 512-bit prime numbers, which are not secure. If in the year of 2022 the server still performs export grade Diffie-Hellman key exchange, then it sends back the server hello message, and you can see that it has picked export grade Diffie-Hellman key exchange because that was the only option given. Man in the middle again intercepts this message, and in place of export grade Diffie-Hellman, it puts regular Diffie-Hellman and sends that message to the client. It also, without any modification, directly relays the server key exchange message, which contains the signature with the base number G to the power B, as well as the 512-bit prime number. One vulnerability we see is that this signature does not contain the type of key exchange used. So the man in the middle does not need to modify anything when relaying the signature. And then the client sends G to the power A, which is intercepted again by the man in the middle. So the man in the middle has successfully managed to downgrade the key exchange to export grade level, and using the NFS algorithm described before, if it has done the pre-computations before, now it can do the necessary calculations to calculate the secret numbers and through that the secret key. The authors of the paper implemented the logjam exploit and found out that of the 539,000 HTTPS sites among the top 1 million web domains, 8.4% of them actually accepted export grade Diffie-Hellman key exchange, which meant that this kind of downgrading of encryption was possible, which in turn, using the NFS algorithm, meant that the encryption could be broken, basically. And among them was FBI site as well, actually. The authors go on to approximate the cost of breaking the key exchange encryption without any downgrading to 512-bit primes. Basically, for 768-bit prime numbers, Diffie-Hellman key exchange can be decrypted by academic institutions or groups of similar means. And for 1024-bit prime numbers, state-level attackers can break the encryption. That brings us to the question, is NSA eavesdropping? We know that they are. Snowden leaks reveal that NSA can break VPN protocol encryption, even though we don't know exactly how. But the calculations show that state-level attackers, and definitely NSA, has the budget and means to use the NFS algorithm to break a key exchange, Diffie-Hellman key exchange, even with 1024-bit primes. So how can we prevent these vulnerabilities? Well, specifically against the logjam exploit, TLS can update its protocol so that the signature sent by the server includes the specific cryptographic algorithm used. And for attacks against Diffie-Hellman in general, servers can increase the minimum key, or the prime number, to at least 2048 bits, which defends currently at least against even state level attackers. And we can also use elliptic curve Diffie-Hellman instead of regular Diffie-Hellman, which uses modular arithmetic. And basically, elliptic curve Diffie-Hellman is more secure while also being more efficient. Thank you for listening.